Hey, thanks for joining us today. In this live stream, we'll be diving into generic and AUTOSAR software architecture modeling using System Composer. Let's take a look at some of the things you can do. System Composer lets you model, simulate, verify, and generate code for software architecture models, including classic and adaptive AUTOSAR. This is an example of a landing gear control system developed as a service-oriented architecture. Function calls are used to trigger the gear to extend or retract, which actuates the gear in the plant model. The sequence viewer can then be used to observe the calls being made between the software components, as well as the input and output arguments associated with them. My name is Josh Kahn, and I'm an application engineer here at MathWorks. I specialize in model-based system engineering, and I'm joined by my colleague Shweta today. Shweta, I'll give you a second to introduce yourself.
Sure, Josh. Hey, I'm Shweta, product manager for AUTOSAR, DDoS, and SOS support from Simulink, and also code generation. Yeah, I'm joining Josh to talk about how software architectures being authored, especially for AUTOSAR in Simulink today. Back to you, Josh.
Great, thanks, Shweta. So starting off with a high-level agenda, we're going to look at software architecture modeling in System Composer, a more specialized version of AUTOSAR modeling, and then we'll have some time for wrap-up at the end with Q&A. So now let's look at software architecture modeling. Today, as part of this, what we're going to do is we're going to create a software architecture, add some profiles and stereotypes to extend the modeling language. We'll define interfaces between our system components and create some software functions, look at what you can do with views capability, and then we'll implement those component behaviors using Simulink and integrate that with an external scheduler. So the first thing we'll do is start System Composer. There are two templates here, the generic architecture and the software architecture. We'll choose software architecture and give our model a name. Aircraft soft, save this into our current directory. So now that I've got this saved, the next thing I'm going to do is open the two common panes we use, the interface editor and the property inspector. These are kind of like your bread and butter here in System Composer. Now we're going to click and drag on the canvas to create some components. We can right-click and drag to duplicate them, change their names, and to add some connections, we just have to drag from the edge. So I'll drag from the architecture root here to create an input port to my I/O processing. And we'll name these aircraft data in and cockpit data in. And then we'll also send those out of the top-level architecture. So we've got aircraft data out and cockpit data out. And then finally, I'm going to create a service interface between my two systems, the I/O processing and landing gear. So I'll single click on the edge and select server port. This is I/O processing, so let's call this I/O server. And I'm going to click and drag to the landing gear system so that I can establish that connection.
Josh, the
Sure.
client and server port looks really fancy. Can you explain a bit more on that? It looks really new.
Yeah, so the client server port is special for software architecture models. And what that lets you do is create a service interface between the two. So rather than just sending data back and forth, you've got an API call structure. So you can specify your function prototype as well as your input and output arguments for those function calls that can be made between the two services.
Okay, cool.
Yep. So now what we're going to do is create a profile. Profiles let you extend your modeling language in System Composer. So rather than this just being a standard component, we can say that this is a software component or what kind of software component. We can associate properties here. So I'm creating a generic software element with a latency property. This is an aircraft, so we'll create a stereotype called DAL component, and maybe that's got a DAL level associated with it. So let's add that DAL property. And then for the type, I'm going to set that to enumeration. And you can make your own custom enumerations here. MATLAB sees it doesn't exist, so it even gives me a template. All I have to do is just fill that in and give it some options here. So we'll say unset A, B, and C. That generates a file in my working directory, and then I can choose a default value format. The next thing I'll do is create two more specialized stereotypes that will inherit from my software components. Here, you can also set your default stereotypes for your compositions. So if I apply the software component stereotype to my root level architecture, then any components I create within it will automatically have this stereotype applied. I won't have to worry about going back and reapplying stereotypes every time I add a new component. Like I'm showing here, we also have inheritance. So you specify your base stereotype. Any properties that you define along the way kind of stack up. And you can even apply custom styling. So Here we'll create our control component, and I'll set that as a software component, and I'll give it an icon and some coloring. The next thing I'm going to do is create some stereotypes for my ports. And this is just to style the canvas, so it's easier to look at the architecture model. We can also use these to add additional metadata if we wanted to associate latency with these or any other properties that we might have from our port. We can do that as well. And now that I've got my stereotypes created, I'm going to save my profile. And then that gets stored as an XML file in my root directory, which can be linked to multiple architecture models. So now we've created this profile. Let's go ahead and import that into our architecture model. And by importing the profile, we can then apply stereotypes. So if I right-click the canvas, I can apply that software component stereotype. It shows up in the property inspector, and the properties that I added to that, I can add instance-specific values for the architecture. I'm going to apply this I/O stereotype and this control stereotype. So now I've got my styling. You can also select multiple elements and apply stereotypes at the same time using the Apply Stereotypes button on the top. So I'll classify these as data ports. And then finally, I'll apply that service port stereotype to my I/O server so that I can see my styling there. Now it's really easy to see what kinds of connections I have between these components. If we wanted to modify this, I can go back to the profile editor. Let's say that we want to associate that latency property with our ports. All I have to do is set the base stereotype and save it. And if I come back to System Composer, now I've got that latency property available on my port. So I'm going to save the model and move on. So now I'll resize the canvas. If you hit the spacebar, it fits the screen. And we're going to add some interfaces. Interfaces specify the data type of the data being communicated between ports. I'm going to use composite data interfaces here, which are like structured interfaces. I can give the elements within those any names I want. Real quickly, we're going to rush through this to kind of establish all of our base interfaces. And then I'm going to create a service interface. And like I was talking about before, this is different in that now we're going to specify function prototypes, and System Composer parses those prototypes and lets you set the data types of your input and output arguments. So in this case, we'll set this in the property inspector to be an enumeration type, and that's going to be our hardware channel mapping. And so what this is going to do is we're going to tell the I/O server that we want to get a value for a certain named signal, and then it'll reference the enumeration to know what channel number that signal exists in. Once I've got my interfaces defined, I can save that to an external data dictionary, and that data dictionary will be linked to both the architecture model and any subsequent Simulink behaviors that we create. To assign the interfaces to the port, all I have to do is just select the interface in the interface editor, and then right-click the ports and choose Apply Interface. As we go through that, you can also see some highlighting showing up, and I'll show that at the end once I get all of this assigned here. So as we click through these in the interface editor, you can easily see on the architecture canvas which interfaces are assigned to what port through the use of this purple highlighting.
This looks cool, Josh. It seems like our latest feature we added, this, especially the highlighting the function ports and the corresponding server ports, right?
Actually, it's been there from the beginning. So regardless of what version of System Composer you have, you can open it up today, assign interfaces to ports, and start clicking through them in your interface editor and see that purple highlighting on your canvas.
Okay, cool.
That was a great question. Thank you. All right, so the next thing we're going to do is add some software functions to our software components. To do that, we're going to open the functions editor from the tool strip. And then we can choose what component we want to add some software functions to. We'll type in our function name here. I'm going to put in process hardware I/O, 1 millisecond. And we can schedule execution rates for these. These rates are used for simulation purposes. And a little bit later, we'll look at how we can integrate this with an external schedule for code generation. So now on my two components, I've got the I/O processing with a software function to process my hardware I/O at 1 millisecond. And then my landing gear system is going to process inputs from the cockpit at 50 milliseconds and then update any indicator lamps in the cockpit at 250 milliseconds. Now let's look at different ways we can slice our architecture model. We can open the views gallery. We can create views, give them names. In this case, we'll say software hierarchy, and we'll filter our architecture to select all of our components. I can switch between a component diagram, component hierarchy, class diagram. So this is different ways of seeing our layout of our architecture, either as an interconnected diagram or hierarchically, as well as any ports, parameters, interfaces, stereotypes, properties, etc. We can also filter more specifically. So here I'll filter on components with a port with a certain stereotype, and then I can filter that down to a certain port with the stereotype applied. And we see a much simpler view of this complex architecture here. So views really give you a dynamic way to kind of slice your architecture to focus on specific domains that you might be reviewing at the time. So now let's look at creating Simulink behaviors. I'm going to right-click my component and choose Create Simulink Behavior. I'll hit OK. And what's going on here is that System Composer is creating Simulink models to back each of these components. It's copying that interface definitions that we've added through ports and assigning interfaces to those ports. And it creates this Simulink shell model. It looks at those functions that we assigned, and it creates these function call subsystems for us, so that as we execute those functions in our software architecture, it actuates any code that any logic that we put inside of these subsystems. We can also see that there's bus element ports along the top, and those bus element ports have the same interfaces that were defined in System Composer. And then finally, for these service interfaces, we can define what happens when a call is made. So I'm going to fill this in real quickly, and I'll pause right here. So now we can see our different parts of our Simulink model. We see our process hardware I/O call right here. We see our aircraft data coming in, cockpit data coming in. And this is using all of that structured interface information that we defined in System Composer. We've also got subsystems over here fully defined for those API calls to our client server ports. Now, another thing that we can do is we can call our client server using these function caller blocks. And in these, we can just specify the prototype and then determine what we're going to pass in and our expected outputs. So you see that the caller block here morphs to fit the same prototype that we defined. We can open up the schedule editor and look at things like dependencies between our functions and our software. And there's also a legend that shows you what each of these different indicators means and the various coloring. If you look at the right-hand side of the schedule editor, you can see the execution order and what is triggering each function to occur.
Josh, can you change the execution order and play with that?
Sure, yeah. So yes, that's one of the things that the schedule editor lets you do, is you can change the execution order here if you wanted to. You can also specify execution order in the function editor by moving those functions up and down as you create them.
Thank you.
And we support both synchronous and asynchronous function calls. So if you wanted to be able to make a call and have it wait until there was processor availability instead of stopping the whole thread, you can specify that as an asynchronous function, and it'll execute when it's able to.
Mm-hmm.
The next thing we'll do is we'll reference our software architecture model. So I've got a Simulink model here, and I added a model reference block. I'm going to add a function call generator and a state flow chart, and we can add some events to that state flow chart. We'll call the base rate of 1 millisecond, and then we'll make events that correspond to our functions that we defined over here in our functions editor. In this case, we'll just make one simple run state where everything kind of gets called in a fixed order. So when we enter, first it calls all of our functions. Then we'll say on every one call of the base rate, we'll do our 1 millisecond function call. Every 50, the 50 millisecond, every 250 millisecond, we'll do our update indicator lamps. They don't have to be one-to-one as long as they're even multiples. And then what we can do over here in the symbols pane is set the inputs and outputs of those. So now they're not internal events. They send something out of the state flow chart. So we'll take that base rate coming in at 1 millisecond, and then we'll connect those outputs to our software architecture model. So now that state flow chart is acting as a scheduler for that software architecture. Then that's everything that I had planned to show today for the generic software architecture model template. And now I'll hand it over to Shweta to discuss AUTOSAR.
All right. Meanwhile, would you like to take some questions, Josh? Let's look.
Sure.
Let's look at the YouTube while I share my screen.
So while Shweta's looking into that, one of the common questions I get is, now that I've created this software architecture in System Composer, can I generate code from it? And the answer is yes, absolutely. So as you build up your architecture models and include these Simulink behaviors, you can include either Simulink subsystem behaviors, subsystem references, or model references. Each of those model references will compile as an atomic unit, so that'll be an executable. Each subsystem reference will compile into the top-level System Composer architecture. And then that generates source code the same way you would generate it for a Simulink model. All right, Shweta, it looks like you've got your slides up. Are you ready to go?
Yes, I am. All right.
Perfect.
All right, let's get into the software architecting modeling for AUTOSAR. So this is the agenda I have for today. First, I thought of give you an overview of AUTOSAR and then the design workflows. So in AUTOSAR, there are two platforms. One is Classic, the other one is Adaptive. So I'll show authoring workflow for both, which looks very similar. And once we build that architecture model, let's talk about the Linux executables from the architecture model itself for the adaptive applications. Then I'll end this presentation with call to action. All right. I thought of introducing you to AUTOSAR by identifying the difference between AUTOSAR as well as non-AUTOSAR architecture. As you see here, in the non-AUTOSAR architecture, the application software and the hardware pieces are tightly integrated. And the layout looks really rigid, and then the application software is dependent on the hardware. Whereas in the AUTOSAR classic layer, it is all the layers has been modularized, and the application software is abstracted from the below level software like basic software services, also the independent of hardware. So in this way, it makes it really easy to reuse for different applications, like you can change the hardware and also change the application based on what you want to do. And it follows signal-based communication and allow monolithic update. So, and then the AUTOSAR Classic is used for traditional automotive applications like powertrain, body control, instrument clusters, and so forth. Then the AUTOSAR org also introduced another architecture called AUTOSAR Adaptive, which is very similar to Classic, but here the application are considered as services on its own, mainly used for autonomous driving, vehicle-to-vehicle type applications.
Hey, Shweta, I've got a question on
sure.
that. So with Classic and Adaptive AUTOSAR, does that mean that if we had Classic AUTOSAR, we need to move to Adaptive, and everybody's moving to Adaptive, or do we pick and choose between them based on what we're doing, and how do we make that decision?
Hang in there. I have a slide on that.
Awesome.
Yeah. But just to give a preview of it, AUTOSAR Classic implementation is all done in C coding, and then as I mentioned, it's used for the traditional applications, but not enough for the high computer intensive applications like a vehicle-to-vehicle communication or the autonomous driving related applications. That's why the AUTOSAR Adaptive standard has been introduced, where it will allow you to deploy each application services independently, not as a monolithic update. You can do selective updates through over-the-air type form. And then the AUTOSAR Adaptive follows service-oriented application, and which allow the services can be deployed dynamically as well as at runtime.
Okay, thank you.
Yeah. So here is a picture of a car. In the today's car, most of the cars on road has got both non-AUTOSAR as well as AUTOSAR classic ECUs. Going forward, AUTOSAR Adaptive based application ECUs will continue to coexist with AUTOSAR Classic. Not necessarily the Classic application has to move to Adaptive. Yeah, so I would say yeah, probably few OEMs have already launched Adaptive ECUs in the car, and you're going to see all non-AUTOSAR, Classic as well as Adaptive ECUs in a car. Yeah. So AUTOSAR is much more than a standard. It is mainly formed by the leading OEMs and suppliers, and it has got several partners. It has about over 300 partners across the globe who come together and develop this standard and make it as an evolving standard and be still relevant to the latest applications related to automotive domain. And MathWorks is an active participant in developing these standards with a focus on how MBD will fit into this picture. All right, now let's move on to the AUTOSAR design workflow. So if you already have an existing Simulink model, you can configure your model for AUTOSAR directly in Simulink, or you can port your architecture model to AUTOSAR as well. I'll talk that in a bit. And then once your application is developed, you can generate C or C++ code, C for AUTOSAR Classic and C++ for AUTOSAR Adaptive using embedded coder. Simultaneously, you can generate AUTOSAR XMLs. And this is bottom-up workflow. And the other approach is you can start from an AUTOSAR architecture where you will define all the data types, runnables, interfaces, and then generate the AR XML, the AUTOSAR XML from there, and import that into Simulink or in System Composer. In both ways, they are tightly integrated, and it's easy to switch between a Simulink or an architecture model, then generate C or C++ code, and that's top-down workflow.
Hang on. So are you saying if I've got my AUTOSAR model in an existing tool, I can take that and still import it into System Composer and Simulink?
When you say AUTOSAR model, right? When I say like a import of an AR XML, that will just have the information about the architecture pieces which you showed in your example, without even adding logic. When you import that into System Composer, right, it will create a skeleton of it, and it may not have a model created for it. You can create a model from an architecture. That model could be in a Simulink model, and then add in your logic, internal behavior per se. So then it will be complete to generate code and AR XML.
So as long as I have an AR XML file, I can bring that into the MathWorks environment?
Yes, that's right.
Great.
Yeah, even if you don't have an AR XML, start from Simulink and System Composer. You can generate AR XML anyway down the line. All right, moving on. So the first question, and oftentimes I get asked, like, which one of these architecture model templates should I use for AUTOSAR workflows? So by the way, this is a Simulink start page. This is where you will get this question. So we support 3 templates. The first one is generic architecture design template. That's mainly for the logical, functional, and physical templates. So where you can compose software and AUTOSAR nodes in this level of architecture. And then Josh used the software architecture model template, so that will help you add client-server interfaces and function editor interfaces. And for this demo, I'm going to use the AUTOSAR software architecture template. Is a software architecture model which will provide purpose-built canvas and resources for AUTOSAR properties. So that will provide out-of-the-box support for both Classic as well as the Adaptive platform.
So if I install System Composer and I don't see that AUTOSAR option there, what am I missing? What do I need to do to be able to get that AUTOSAR template in the Simulink launcher?
Yeah, great question. You need to have AUTOSAR block set being installed. Then it will give that option to get the AUTOSAR template. Yeah.
Perfect. Thank you.
All right, so we support two workflows for AUTOSAR. So as of 2019B, you can use the AUTOSAR template if you already know you are doing AUTOSAR. Additionally, if you already have existing architecture model, could be Josh's architecture model. So in the release 13B, we allowed you to export them to an AUTOSAR architecture model. So this will handle the complete hierarchy, including linked components, and it will make it easy to be able to port from another software architecture to AUTOSAR architecture. So for the sake of this live stream, we will use the first workflow where I'll start modeling AUTOSAR architecture directly in System Composer. All right. So yeah, in order to author the AUTOSAR architectures in Simulink, I'll start with collecting my Simulink model. I'm following a bottom-up workflow. I'm building a throttle position control and I have all the logic implemented for the throttle sensors and also the monitor. To get started, I'm going to Simulink start page and I'm using a software architecture template for AUTOSAR. You can see that AUTOSAR banner is already being used. And at the top, you can see options to import AirXML, and on the left side, you can see you can drag and drop the components, compositions, and also the reference implementations for the basic software services. Okay, so now let me clear this default content from the window so that I can construct a new composition since I already have a bunch of sensor components models. So I'll just going to flush this out and then create a subcomposition inside this composition template. When I say composition, composition has multiple components in it. So at the top level composition, I'm bringing in a subcomposition so that I can add my sensor components inside that. All right, I'm calling it sensors. TPC primary. Yeah. Under the sensors, I'm creating multiple sensor components. Here I can create a model or link to an existing Simulink model. Since I already have a model, I'll go with that approach. Or you can create a component model from an AirXML. That's by importing that AirXML into Simulink. So let me go ahead and link to the existing Simulink model, which I already created. Okay, that's my throttle sensor 1. Notice that it is a sensor actuator component. The banner has changed. And it also identifies whether it's an application component or complex device driver and so forth. But here it is sensor actuator component. So similarly, I'm adding other sensor components. First, I created the subcomposition and then added the logic from Simulink. All right, and now I'm adding all the necessary interfaces. Okay. The composition again reuses all the great things you like about Simulink's intuitive editing capabilities. So I've assembled our composition hierarchy. So I updated the model to flush out any integration issues. All right, all good to go here. Now let me save this model and call it TPC composition.
Hey, Shweta, we've got a quick question here.
Sure.
Someone said, importing ARXML architecture as a composition doesn't include interfaces in the architecture editor. What is the reason for this?
Architecture not includes interface in the architecture editor. Oh, so in this case, I did not import it in this demo since it was a bottom-up workflow, right? I created a component. That's why I did not have interfaces that were exposed or beyond this composition. But to your point, when you do the top-down workflow, when you are importing AirXML for compositions, so it will have all those interfaces.
Awesome,
Yeah.
thanks.
All right. Okay. Now let me link to the requirements to make sure I have all the implementation are as per my requirement. So I'm using Simulink requirements. So it has got 4 sensor and actuator components. To make sure it is there, I'm just dragging it. We can, yeah, looks like, yeah, it is all being linked as per my requirements. All right.
So to link a requirement, I just have to click and drag from the requirements editor onto my component or my port?
Correct. Yeah.
Great.
Okay, now the natural next step is to simulation. Before that, I would like to enable the functional connections. That means this model may have calls to the basic software services related to the NVRAM or diagnostics managers. I see that there are connections. It is looking for the reference implementations. So I am dragging the diagnostics services reference implementation and also the NVRAM. Okay, by updating the model, it will make necessary connections. Now I can configure the IDs for the diagnostic service components. All right. To simulate this, I'm adding this reference implementation for the diagnostic model again. So we'll add a model reference block. Yeah. So inside this, I'll just connect to the TPC composition, which we just created it.
Oh, so this is just like with the software architecture model.
Yeah,
then.
yeah. I'm creating a test harness to make sure my algorithm is working as per my requirement. And at this level, you can enable a schedule editor that will allow you to visualize the order of execution, which Josh already showed, and I'm changing the order of execution as per my requirements, and I can see and visualize the results when I do the simulation. If I'm not happy, I can come back and always change it. So this is a nice place to stop and see and verify your execution order. Yeah, the input sensor value is following the output sensor value. All right, I'm good with this. Now it's time to generate code in the ARXML. Yeah, it will create a separate folder for it. It's a zip file, and I started building my model. Notice that I'm building all the components. I have got 6 components under this compositions as well as subcomposition.
And so what you were saying earlier was that this ARXML includes the structure or the architecture of the model, but not those Simulink behaviors, right? So those will still be separate from my ARXML?
That's right. I will generate the code in a separate folder and the ARXML in a separate folder. ARXML, it's just merely an architecture piece. Whatever the logic was implemented in Simulink, it will all be in the C code. All right, I'm almost done with building my model. Okay, here you can see I've created 2 folders under the zip file. One contains the ARXML, the other one contains the source code. Let me dig into this ARXML file. Notice that I've generated ARXML for all the individual components as well as the composition. Yeah.
So if I have an AUTOSAR architecture and then I've got one that's created as just a regular software architecture, can I integrate those together?
That's a great question. That's our vision. Yeah, not right now, but we are working on it. And then you can see the C code as you saw. So if you want to try this example on your own, we have a documentation and it's a shipping demo. I would encourage you to try that. All right. Yeah, so in the example what you saw, we had several components and we already created a composition from there. See, if you haven't created a composition, what do I do, right? So in that case, you can create a composition from the components itself, like it is shown in this slide. It has got 4 components of 4 sensor components. I'm grouping that as a sensors composition under that, that will allow you to save this composition block as a separate AUTOSAR architecture model. All right. So, and then
looks like we've got another question here, Shweta. How do you define computation methods in System Composer so that it will translate into a computation method in the AUTOSAR block set dictionary table for the software component?
Yeah, so the AUTOSAR dictionary, that's what my next demo is about. Yeah, I'll answer that through this demo. Yeah.
Awesome, thank you.
So I have the right audience. They're asking the questions the way I'm showing.
Yep.
Yeah. All right. So here I'm creating a data dictionary, the architecture data dictionary, which is again reflected in your Simulink model, which is nothing but the AUTOSAR dictionary related information, and where you define all the interfaces, data types as I'm showing here, and also there is an option for constants, and then defining the different data types as you see here, and then also option for computation methods.
I haven't seen this architectural data editor. Is this
Yeah,
new?
Very new. Recently. Okay. Yeah. Yeah. This is where all the the architectural information is being handled and centralized between the architecture model and also the Simulink model.
This looks like a much easier way to manage my architectural data than using the Model Explorer.
Exactly. That's why this feature comes in very handy. All right, that's about the architecture data dictionary. Now let's move to the top-down workflow, where I am starting from an ARXML created from a third-party tool. All right, this is my ARXML.
Does this have to be a specific version to import into System Composer?
We support several versions of it, all the way from 4 dots to the latest 2111. Okay, now I'm importing that ARXML into the architecture model. All right, so I'm opening import from ARXML option right here. This will open up an importer app, and over here I'll browse for the ARXML file I would like to import to. Notice that it's a composition ARXML. Yeah, over there you can choose your own data dictionary, or it will just create one over here. All right, so now I'm creating an architecture model right from the ARXML.
So how many files do I get when I do this? Do I get one System Composer file and a data dictionary, or do I get a collection of files? What does that look like?
Since it's a composition description file, right? Notice that one composition architecture model, and that has got several components in it. And when I chose, I did not choose to have a data dictionary or anything like that. Yeah. So inside this, it just created a skeleton model, right? I can link to an existing Simulink model. And over here, you can choose the schema version if you want to change it. So that had 4.2, and we retained the same version. So, and it has created a Simulink model, but that has got, it's just a skeleton. It doesn't have any internal behavior or an implementation logic. So once you add your logic, then it is good to generate code and ARXML from here, like we did in the bottom-up workflow.
So it looks like importing that ARXML file really fast-tracked us through that software architecture workflow that I showed earlier.
Exactly. It will bring back to that workflow. Yeah. All right. So, and also there is a popular customer use case to support ECU extract, where you can create your ECU extract right from the architecture model. It's very crucial for the automotive customers, because this contains the information from the system configuration description needed for a specific ECU, and we support that at import as well as export level as well. So I see another question coming up. The question is, when importing an ARXML which is generated by other tool with stereotype applied, the stereotype get deactivated. Is there a way to keep stereotype on software component which is created using external ARXML file? Yeah, so that one, in this example, I did not have that stereotype information, so that's why I did not highlight it at all. And again, really it depends on the what version of MATLAB you are using to enable the stereotype. We need to look on that.
So that importing those stereotypes is supported in later versions. Is that what you're saying, Shweta? Okay, perfect. Thank you.
All right. So Delphi Technologies, they've already used the AUTOSAR software architecture workflow, which I just showed for their multi-core electric powertrain software, and they presented this at one of our conferences. Yeah, it's a nice user presentation for you to go through this and learn more on how a supplier has embraced this workflow for their production project. All right, so that's all about AUTOSAR Classic. Now let me switch to AUTOSAR Adaptive. Yeah, so in the AUTOSAR Classic side, in the architecture model that had got AUTOSAR banner and C was there. When you go with AUTOSAR Adaptive, notice that it will have a banner of A. That means adaptive. Okay, so in the adaptive architecture model, we can author ports for events communication. So like here, this user light switch, and then also for methods communication, like this for client or service required port called headlight. And here it's using the client server ports, which was used by Josh earlier in his aerospace example. And then over here, the architecture data section is also available to author and manage interfaces for both the event and method communication respectively, and also assign the data interfaces. So like in the light switch interface, here map to the event communication, while service interfaces like the light service contains method. So in addition to this, the powerful workflows that are used from classic AUTOSAR architecture modeling are also available here as well, like linking to your existing component models, importing from ARXML, or creating behavior models with skeleton implementations from your either sketches, including ports as well as interfaces. Okay, now I've used the same workflow to assemble a simple light system. Once I'm done building it, you can simulate this scenario and verify the algorithmic implementation using the simulation capability available in Simulink. And then I can also export this architecture model to generate C++ code and ARXML for the components and the composition, as we did in AUTOSAR Classic as well. Okay, so here I have using the software architecture template to build my adaptive architecture model. Yeah, before I start adding components, let's bring in some interface definitions that we have received from our architect. All right, these are defined in a data dictionary and can be accessed via the interface editor at the bottom. In addition to the docked editor, I can also open a standalone editor that allows me to manage multiple dictionaries and provides authoring support for interfaces and data types. Okay, we can see a data interface called light switch with the single element there, and then service interface light service as well. All right, now let's start building the adaptive components. I'm creating a lights manager here. and over here I am linking to an existing Simulink model. All right, and the event is coming from the outside of the system, and so I'll connect that with the right port. Yeah, and then yeah, that's about the light manager. Then I need to add the server to implement the light service. Then probably call that as a light controller. So I do not yet have an implementation for it, so that I'll go ahead and create a skeleton model.
What does that mean, model reference export function, when it creates the skeleton?
Yeah, it is looking for the this function port, since it is using the Simulink function for that. It didn't have that, right, initially when I created it, so it will look for the Simulink function. That's the beauty of using this client server port, and that will use the function port and the port scoped Simulink function with that.
So then I'm not just stuck with rate-based models.
Exactly, right.
Nice.
Yeah, so MATLAB is investing a lot in supporting this service-oriented architecture. So AUTOSAR Adaptive is based on the service-oriented methodology. So all right, that's about modeling AUTOSAR Adaptive architectures in System Composer. So once you're done modeling, yeah, as I did it in AUTOSAR Classic, I can generate code. Here it is C++ code, and then I've also generated ARXML files containing component descriptions, as well as the composition descriptions, and then related to data types and interfaces, as well as the deployment configurations, which is named as manifest files, and the service instance manifest files. All right. Now, I would like to talk about deploying Linux executables right from the adaptive architecture model. So here I'm using I'm creating a deployable executable file right from the architecture model. So this will build all the component models and generate deployment configuration, which will be copied to the host. In this case, my Linux machine is being used, and that's my target. And then when you deploy it, we can use this log viewer to check events and also use the monitor and tune option to view my results. All right, so this makes this deploying multiple adaptive application process lot straightforward. All right, so that's about my adaptive application authoring. So going back to Josh's question, is there a requirement for customers to move from AUTOSAR Classic to AUTOSAR Adaptive? I said it really depends on the applications, but I'm seeing a few customers who would like to migrate their traditional automotive applications, which use a signals-oriented communication, to service-oriented to be more agile and help support this high computer intensive applications. So for that, we wrote an article about how do we migrate this traditional signals oriented automotive applications, which could be compositions in nature, to generic service oriented architecture applications, and also to AUTOSAR Adaptive services mainly used in the software defined vehicles applications. So for this workflow, we used System Composer as a way to start to author your signals-oriented applications, and ripped apart to make it more service-oriented, and then generated code and deployed the C++ code reconfigured for AUTOSAR Adaptive. I would definitely encourage you to read this article to learn more about how do you migrate such traditional applications to adaptive services. All right, this brings us to the almost end of our presentation. I would like to end this by giving some actions to do. Yeah, definitely encourage you to try this shipping examples which will enable you to understand the software architectures workflow with Simulink and System Composer for automotive as well as aerospace example. And that's all I have for now, and I'll open it up for more questions.
Just real quick, I'm going to do a little plug here. We also have training available for AUTOSAR and System Composer. So if you're looking for ways for your organization to be able to adopt some of these tools and learn how to use them better, or even get more exposed to them, we've got training options. So we can do on-site training. You can visit us in our Natick or Novi offices for training. And if you have existing solutions that you're trying to migrate into System Composer or Simulink, and including AUTOSAR, we also have consulting available to help you work through some of those challenges, and application engineering support, where we can kind of work with you one-on-one, small proof of concept programs to figure out what this looks like in your workflow. And now I guess we'll switch over to Q&A.
Yeah.
So feel free to ask in the chat. We are getting fed any questions that come through.
Josh, looks like there is a question on SysML. Would you like to take that?
Sure. So we do support SysML interchange with System Composer. Will probably be a topic for another live stream, but absolutely. So what I would say is reach out to your sales rep and just let them know that you're interested in finding out how to collaborate between SysML models and System Composer, and we'd be happy to have a follow-on conversation about that. Just in case you haven't been following the chat on YouTube, a lot of what we've shown today has been linked in the chat there. So we've included examples for AUTOSAR, software architectures, and also a link to our architecture solution page.
Okay, I see another question coming up. The question is, do we need AUTOSAR software installed explicitly if we have AUTOSAR blocks from MathWorks? Not really. You do not need, there is no such AUTOSAR software per se. You can start creating your own algorithm right in Simulink by modeling, and then just configure it for AUTOSAR properties using AUTOSAR blocks. That's more than enough to develop your application software for both classic as well as adaptive. All right. Yeah, I think we are almost at the end of our of the scheduled time for this live stream. If we don't, looks like we are good with questions. Probably we can end our live stream now. Yeah, thanks for asking all the great questions, and definitely thank you for your attention. Have a good one.
Yeah. Thank you, everybody. It's great talking to you.
Bye.
Bye-bye.